Hello everyone. In this video, we're going to derive the heat diffusion equation for the Cartesian coordinates using a cube example. So let's say we're given a cube and the cube is going to have a sides of lengths dx, dy, and dz. Okay, so we want to find out the heat diffusion equation. So let's say there's going to be heat going in and heat going out of the cube is going to be qx plus dx, which we can also express as which is almost equal to qx plus small change in flux over small change in x multiplied by dx, which can be said as a rate of change of a flux of a flow rate and a particular dx. Okay, and so there's going to be the heat going in and heat coming out of the cube, right? So the heat stored inside is going to be the heat coming in minus the heat that is coming out of the cube, right? Which is going to be the qx's are going to cancel, so we're going to have negative qx dx, right? And we also given that the energy stored inside of a cube is going to be the rho Cp times the small change in temperature over small change in x times dy times the volume, which is going to be dy, dx, dy, and dz. Right? Okay. So the next thing we can do is so we can find out the flow rate of our heat flow of our cube, right? So the heat flow is going to be the flux times the area, right? So for example, if we're going to consider the x direction, so the motion in x, the area is going to be dy over dz. So we're considering this area right here. Okay, which is going to be, so we found the dx. We can find the qx from the Fourier's law equation, which is going to be the negative k delta t over delta. So we're considering the x direction, right? So delta x times dy dz. And we can do the same thing for other exercises. So we can determine the same flow from in y direction and z direction. So qy is going to be negative k t. It's the small change, sorry. So it's going to be like small change of temperature over small change in x. Small change in temperature over small change in y. So when we're moving in y, that's going to be the dx over dx times dz, and for z axis that's going to be negative k, small change in temperature over small change in z distance times dx over dx times dy, which is going to be the area, right? Okay. And there can also be a heat generation inside of the cube, right? So we can just say we're going to have a q dot, and that's going to be our heat generation inside of the cube. Okay, and the sum of the all flows that are going to be inside of the cube should be equal to the energy stored inside of the cube, right? So what we're going to do now is, so we found this equation, right? So we're gonna apply that energy that is left inside of the cube. So we found Qx, Qy, Qz for each of the directions, right? So I can write it as, so that's gonna be the negative small change in Qx, which is gonna be this equation, right? And the negative, negative, so they can cancel, and so I can get rid of negative sign. So that's gonna be, okay, that's, okay, I'm gonna write it down as, so x. So the inside I'm gonna have the k times delta t over x, and that's gonna be dx, dy, dz, right? So I can do the same thing for each of the direction, and the sum of all of them should be equal to the energy stored inside of the cube, which is this thing, right? So if you can notice, each of the terms are gonna have dx times dy and dz. So I can divide the whole equation by that number so that our equation is going to be simplified, right? And on the right side, I'm going to have the density times Cp times the heat coefficient times the small change in temperature over small change in x times the volume, right? So if I divide the whole both sides by dx times dy times dz, I'm going to have, so I'm going to have this, so that's going to be the square second derivative of temperature times k, that's for x, times k times small temperature, second derivative of temperature respect to y, plus second derivative of temperature respect to z, and we can also consider the heat generation inside, right? And we said our heat generation is going to be Q dot, right? And the whole thing should be equal to the energy stored inside, but we divided it to dx times dy times dz, which is the volume, right? So that's going to be the density times the coefficient times the small change in temperature over small change in. Oh, I just noticed that I made a slight mistake. This was a small change in temperature respect to time. So I'm gonna have to write that. Okay. The next thing we can do is we can divide everything by k. Just for the simplification where k is constant, because usually if we consider a different case, our example would be very difficult for the calculation. So we're gonna consider that the k is constant and divide everything by k. So what I'm gonna have is second derivative of temperature respect to x plus second derivative of temperature respect to y plus second derivative of temperature respect to z plus energy generation over k equals density times constant over k times small change in temperature, so derivative of derivative of temperature respect to time. Okay, and then we know that we have a term alpha, and that is k over the density times the capacity, right? And using this, I can change it to 1 over alpha. So the heat diffusion equation we're going to have at the end is going to be the second derivative of time, second derivative of temperature respect to each side plus the heat generation over k equals 1 over alpha times delta derivative of temperature respect to time. So the last thing we derived is going to be the heat diffusion equation in Cartesian coordinates. So we use the cube example, which has in 3 dimensions, so we considered the motion in x, y, and z direction to find the heat diffusion equation in Cartesian coordinate. So that is going to be our answer. Thanks for your attention.